Okay, thank you, Lucilla. Good morning, everybody. So today I will present some functionalities available in the PITHIA Science Center that allows you to access results from ionospheric prediction models. Yesterday and the day before yesterday, you have learned a lot about ionospheric storms and traveling ionospheric disturbances. So I will just present here a very short review, but I will focus on the theory behind the specific models that are registered in the PITHIA eScience Center. And these two models are, of course, the IRI, which is the reference model for our community. And I will also present the SWIFT model, which is a regional Stormtime model. And the philosophy of SWIFT is totally different than the philosophy of IRI. SWIFT is not a climatological model, it's a real-time forecast model that provides forecast at specific location for the next 24 hours. But this is still an empirical model, as also it is IRI. Then I will present some detectors that are available through PITHIA Science Center for traveling ionospheric disturbances. And these detectors are available through the TechTide zoo of TIDs. We have there a large number of methodologies that detect TIDs. But again, here I will focus on some specific methodologies for some reasons that I will explain later. Then I will show you the resources available through the Science Center. And finally, I will suggest some exercises for the groups who will decide to follow this work. Now, I will start this presentation with the PROL's Phenomenological Model for Ionospheric Storms. This is a very basic model, fundamental model, according to which the ionospheric storms are the result of in-house joule heating globally. And this produce a thermospheric storm, and the thermospheric storm through the coupling is producing the positive and negative ionospheric storms. This model considers very carefully the local time-dependent scenarios, according to which, depending on the location of the observation point, the effects of the storms of the ionospheric storms are different. So, the station 1, for instance, here in this picture, which is located in the afternoon sector, during the expansion phase, which is expansion phase is here is this cartoon. Now does not experience the effect of a negative storm, whereas station 2, which is in the morning sector, observes the negative storm because it is affected by the composition disturbance zone. And now, as you can imagine, as the Earth rotates, the location, these locations are changing position in respect to the composition disturbance zone. And this explains the positive and negative storm effects that are detected in each station. Now, for the positive storm effect, this is a result of traveling atmospheric disturbances that propagate from the auroral zone to the lower latitudes and this disturbance propagates with storm-induced meridional wind pushing ionization upward along geomagnetic field lines. Now, what is not fully explained by the Prohl's theory is the observation of nighttime positive storm effects, which are detected very often. And according to a theory that was proposed by Fuller-Orwell back in 1994, this positive phase is driven by winds before dusk and rotates to the night side. And this is why, for instance, you see in this storm, which is analyzed here, in this storm, which is analyzed here, which is a relatively strong ionospheric storm. Here you can see below the deviation of the FOF2 in respect to the median values %. And you can see that in some European stations at night, this star here indicates the midnight. So for some stations, the positive effect at night, at midnight, is very, very strong. And also this positive effect at night is also seen in some stations in US, in Boulder, for instance, here. And this is the effect of this winds, of the winds before dusk that rotate at the night side. And this is why in a publication that we had years ago, we added a fourth phase in the Prohl's model, which is this one, and explains this nighttime positive storm effect. Now, this is the theory behind the storm, the local time effect in the ionosphere. Now, the IRI, as I said, is a climatological model. It is a reference model for our community. And it provides the most important plasma parameter in the median values originally, and this is a list of the parameters that are provided by the IRI model. The IRI relies on a huge database with data from different sources, from ionosphere, from coherent scatter radar, topside sounders, in situ measurements, rockets, and so this is why it is really a reference model. It is very important to say that the IRI provides the electron density profile. Very also important for our investigations. It is of critical importance to have a reference electron density profile reconstructed from the bottom side up to the top side, and this is what IRI is doing using Abstein functions for the height variations. Okay. Now, some additional IRI capabilities. The IRI developments have the goal to move from the climatological representation provided by the standard IRI model to a description of real-time or past-time ionospheric weather conditions. And these are based on the empirical ionospheric stormtime correction model and on the IRI-based real-time assimilative mapping, IRTAM. Now, here I will focus on the empirical ionospheric stormtime correction model, which is a model embedded in IRI, and it is run. It is provided by default when you ask results from the IRI portal. The RTAM is an independent model, which is based, of course, on IRI, but it is independent. And this model will be presented by Ivan Galkin in a next presentation. Now, the empirical stormtime correction model is proposed by Arroyo, Pradere, Fuller-Rowell, and Codrescu in 2002, and the model is based on a new index that was developed to characterize the intensity of the storm by integrating the previous 33 hours of AP weighted by a filter, and the storm ratio of FOF2 is provided as a function of geomagnetic latitude, and you see here the results. So the output is the FOF2, the correction in the FOF2, which is considered by IRI. Here we have to be careful, of course, because according to the developers of this model, the model provides significant improvement for equinox and summer, but in winter there is no quantitative.
Sorry.
In winter, there is no quantitative improvement. So when we analyze the IRI results, this has to be taken into consideration. Now, the second model is the SWIFT model. SWIFT stands for Solar Wind Driven Ionospheric Forecast. The concept of this model is to use as driver the solar wind magnetic field at L1 point contributed to forecast the high latitude joule heating 1 hour in advance. Now, the SWIFT model has 3 components. The 2 basic components are the TSR algorithm, which is the time series autoregressive algorithm, which provides the forecast of the ionosphere under any conditions up to 24 hours ahead, and the STEAM algorithm, which is an empirical stormtime ionospheric model, and it is activated only when we have ionospheric storm conditions. The third component of the SWIFT is the alert detection algorithm. This algorithm considers the measurements of from the spacecraft at L1, analyzes the magnetic field component in the solar wind, and based on some specific criteria, provides an alert, a storm alert. Since the storm starts to provide some disturbances in the ionosphere 1 hour after the detection of the alert at L1, for 1 hour after the alert, the SWIFT provides a forecast based on the TSR algorithm, because we consider that for the first 1 hour, the storm is not arrived yet in the Earth's ionosphere. After 1 hour, the STEAM model is activated. Now, regarding the alert detection criteria, to define the alert detection criteria, we have done some empirical tests with superimposed epoch analysis and with literature investigation. The criteria that we have computed are 2. The first is concerning the IMF, the interplanetary magnetic field B. This should record either a rapid increase denoted by the time derivative values greater than 3.8 nanotesla per hour, or absolute values greater than 13 nanotesla. The second criterion is that the IMF BZ component should be southward directed, either simultaneously with the B increase or a few hours later. And for intense storm conditions, we consider that these occur when the BZ is less than -10 nanoteslas for at least 3 hours. And here you can see in this diagram here the results of the super epoch analysis based on the analysis of many storms, more than 40 storms. And based on this analysis, we have validated these criteria that have been already proposed in the literature by Gonzalez and Churutani in two past publications. Now, the second part of the model, of course, is to calculate the empirical functions that should be valid when an alert is issued. And for this reason, we have divided the ionosphere in two latitudinal zones, those that are greater than 45 degrees and those that are less than 45 degrees, and in four local time sectors: the morning sector, the pre-noon sector, the afternoon, and the evening sector. And so based on data, atmospheric data from past storms, we have calculated the response of the ionosphere following these alerts for the next 32 hours, I think this is the initial analysis. And we see that there is a different polynomial polynomial equation for each sector. And these functions are applied now by Swift model as soon as an alert is issued, consider also the local time of the specific location. First, verification of Swift. We have published many papers to validate Swift performance and to verify Swift performance. This is just one example that shows the mean relative error from the TSAR model and from steam predictions over 4 locations in Europe: Chilton, Julius, Rome, and Athens. And you see that with the red line is the steam mean absolute relative error. And this is very close to the mean relative error of TSAR for 1 hour ahead, which means that the error of the model is the lowest possible, or consider that steam provides the predictions for the next 24 hours, of course. Now, some issues to consider about Swift performance. We have seen that because Swift is developed based on the analysis of storms that occur from 1980 until 2000, some functionality, the performance of the model is weaker when the storm, the geomagnetic storm that drives the ionospheric storm is not very intense, and it's also weaker when the driver is not a coronal mass ejection, but it is a high-speed solar stream. This means that we have to revisit the criteria for the alert, but also the functions, the coefficients of the model, and apply some updates based on the analysis of recent geomagnetic storms. Considering the alert criteria, we have done an additional analysis lately, and we have divided the performance of the model based on successful forecast, successful alerts, and missed alerts. And the missed alerts are again divided into categories. Those are missed but are related to coronal mass ejections, and those are missed but are related to non-coronal mass ejections. As you see here, this is the first missed alert categories and the second missed alert category. And this is our successful alerts. Now, what we have seen is that in the case when the alert is missed, we have some important variation in the BY component of the IMF in both cases. Whereas when we have just a CME and it was successfully forecasted, the BY component shown the most important variation in the IMF, and but the BY component was not so importantly varied. So, based on the original Gasofu theory, we think that we have again to consider also the variation of the BY together with the variation of the BZ. Because the BY component is considered in the coupling of the magnetosphere with ionosphere based on this fundamental equation. These are some issues to consider when you use the Swift model results. You have to consider if the driver of the ionospheric storm is a CME. This is very important, or it is another structure in the interplanetary magnetic field that caused the geomagnetic storm. Now, we'll show you now some examples on the performance of the ionospheric prediction models. This is the storm occurred in January 2023 with start time at 2 o'clock at 4 January 2023. This is the start of the storm is indicated with a red line here. These are the magnetic field components in the IMF, and this is the DST index. So here you can see the performance of the Swift model together with the performance of the IRI model for Athens station and for Julius station. So Athens is at the lower latitude, Julius is at the mid latitude. So here we have other coefficients of the Swift model in these two cases. So you see that for Athens, the Swift model performs quite well. The IRI a little bit overestimate the FOF2, and this line indicates the observed FOF2. These are automatic scaled FOF2. This is why you see these peaks here, these outliers. And for Julius, this is the response of the model. The model is here, the Swift model, and the IRI is here. It's with a gray line. IRI performs better than Swift for the first day. The second day, the performance is maybe equivalent, I would say. And this is not a strong storm. This is a weak storm. DST was minus 60. Now, another example is the storm that occurred in March 23 of 2023. This is a strongest storm, a more intense storm. DST reached minus 150. And here are the IMF conditions, magnetic field in the solar wind at L1. According to the STEAM alert, we had two alerts. One at the first alert at 1400, second alert at 1700. And here are the results of the model for Athens and for Julius again. For Athens, there is an underestimation from the Swift model. IRI performs better, a bit better. For Julius Roos, IRI performs worse, much worse. Swift is closer to the observed values, but of course, even Swift model was not able to forecast the magnitude of the negative storm that occurred in Julius Roos as a result of this geomagnetic storm. And the third example is on 23 April 2023. We had an even stronger geomagnetic storm. This was the stronger among the three storms. DST reached the minus 200, even exceeded, and we had two alerts at L1. So these are the results for Julius Roos and for RAL. Both stations are at the middle to high latitudes, and for both cases, Swift predictions are much closer to the observed values than the IRI predictions. This is, in my view, in my understanding, in my opinion, this is why this storm is very intense, and Swift had the possibility to perform, and this is why had the possibility to perform much better than IRI, of course. Now, the second part of this talk has to do with traveling ionospheric disturbances. This is a simplified view of what travel ionospheric disturbances look like in the ionosphere. This is a simulation. So if you consider a pool, this is the water in the white pool, but if you look closer, there is something always going on. There is always a movement, and this is these are the waves that we see in the ionosphere as medium-scale TIDs and even worse as large-scale TIDs. Now, large-scale TIDs have been predicted decades ago by Francis, who showed that the average fluctuations of the auroral jet are sufficient to generate freely propagated atmospheric gravity waves, which should be detectable at large distances as traveling ionospheric disturbances. And this is here you can see the traveling ionospheric disturbances detected by using TC, the trend TC, for the Halloween storm over US. Now, let's see a more recent event, which is the St. Patrick storm of 2015. And this is the first super geomagnetic storm of the 24th solar cycle. Now, this storm started with a CME observed by LASCO on the 15th of March. And here you can see the coronal images from SOHO. Now, the CME propagated, these are the early runs, and propagated and arrived on the Earth many hours later. This is the effect of this CME in the magnetosphere, and this is the impact as shown by tech maps. This is publication by Claudia Boyce et al. Of 2016, and here you can see the tech variation with time and latitude for the European, for the Asia, for the African, and for the American sector, together with the DST index. And you can see how important variation is caused in the TC as soon as the storm started here. So we have important, very noticeable variation over the American sector and the African sector, but not so important variation in the Asian sector. Of course, the next day we have a negative storm in Asia, and also negative storm over American sector. In Europe, we had on almost medium conditions. These are the results from 4 European stations over Chilton, Julius Roos, Ebre, and Athens. You can see with the red line, with the green line, you can see the observed FOF2. With the blue line is the reference FOF2, and here the references to FOF2 is provided by the SIR model, and with the yellow line is the F minimum from the ionograms again. So this geomagnetic storm produced very large fluctuations in the FOF2 in all the stations, with some positive trend in most stations, except from Julius Roos, who experienced a negative storm in the evening sector. Here we can see this behavior also in these geograms, which is latitude, which is the evolution of the detrended tech with time and with latitude, and we see clear TID signatures from the auroral propagating towards the lower latitude from both hemispheres. Here at 40 degrees, we had, for instance, the example of the Ebro station in Roquetes, who also experienced very large fluctuations in the height of this iso-ionic contour plots, and this is compatible with the geograms that are shown here in the paper by Claudia Boyce. Now, going from the large-scale TIDs to the medium-scale TIDs, medium-scale TIDs is another phenomenon, totally other. The drivers for medium-scale TIDs are mainly the lower atmosphere disturbances, and these are can be also analyzed also with Digison data, but mainly with tech data, with and the best way to observe medium-scale TIDs is the continuous Doppler sounding, which was first installed in EAP in Prague. And this is a great tool to study medium-scale TIDs for climatological studies, but also for case studies. Here, for instance, I just present one example of medium-scale TIDs triggered by a very strong earthquake that occurred in Japan on 11 March 2011. I don't know how. Can I click here? Is there a way to click here? To click on this map? Yeah, okay. Yeah. Just to show you, if you click again. No, go back. If you push here. Yeah. Just to show you how the waves are generated from the epicenter and propagated over the area. Here we are in Japan, but these waves were propagated and recorded by the continuous Doppler sounding system in the Czech Republic and in South Africa. And here you can see the recordings from the CDSS from this same event. And this is why I strongly recommend that if you want to study medium scale TIDs, this is an excellent tool. Now, coming back to in general possible methods to detect large scale TIDs, we have developed in the frames of a past EU project, the TechTide project, a portal where you can find many results based on many different methodologies for the detection of TIDs. I would like to stress your attention on the fact that we have here results from individual sensors and indicators. Indicators means that the methodology do not provide you parameters for the does not provide you characteristics of the TIDs, but just gives you an indication that the next hours Europe will be affected by TIDs. The result, the methodologies for individual sectors gives you characteristics of the TIDs detected over Europe in real time and also in archive mode. Okay, so here is one possibility to see results from TIDs. Now, how TechTide works in general? In TechTide, we have 8 basic methodologies. Each methodology is based on a specific type of observations. So we have the HFTID method, which is based on bistatic digison to digison measurements. We have the HF interferometry, which is based on digison measurements in monostatic mode. We have the spatial temporal GNSS analysis, which is based on tech data. The GNSS tech gradient, which is based again on tech data, but this gives you an indication for forthcoming TIDs. We have the 3D electron density distribution model, which is based on digison data ingested in a model, which is empirical model based on topside sounding data. We have the HDI method, which is based only on ionograms. We have the CDSS-TID method, which is based on continuous Doppler sounding data, and the AATI indicator, which is based on tech data. And the idea is to collect the characteristics extracted by all these different methods and combining the result to assess based on the conditions in the atmosphere and in the magnetosphere to assess the criticality of TID disturbances. Some some examples from the TID products are shown here. For instance, we have a moderate geomagnetic storm occur on the 5th of August 2019. This is a storm where DST reaches the -60 nanoteslas, and these are the results of the AATR index. This is an indicator. The AATR is along the ArcTech rate indicator, and start to increase together, almost together with the DST degrees. And at the same time, the GNSS tech gradient shows some indication of disturbances starting from the auroral oval and moving to the lower latitudes. And this is the corresponding map the day before, during a quiet day, but at the same local time. And here is another example, another product which is provided again by TechTide, which shows, actually this product was recommended by EGNOS, and this is why we have designed this product. This shows the electron density at specific height at 200 kilometers, 300 kilometers, 400 kilometers, and so on. And under quiet conditions, these maps are green, which means that we are at medium conditions. But when we have storm conditions, the maps are becoming either negative or are becoming red or blue or both, depending on the latitude that we want to check. And this is an indication that a positive storm is going on or a negative storm is going on. Now, for the same storm, 5th of August 2019, we have also the results from the D2D method. The D2D method, as I said, is the result extracted from bistatic operation between two digisons. And here we have the link between Turb and Roquette, which identified at the reflection point a stronger TID, and the characteristics of the strong TID are plotted here. So we can see the amplitude, the Tobler, the zenith, and the azimuth angle of this TID. And finally, here are the results of the HF interferometry method, which are plotted over Turb. Turb is here, and we have identified TID activity that started at 12 and increase for the remaining of the day. Okay, these are about medium scale TIDs. Okay, I would like now to summarize regarding TIDs. In TechTide, I would recommend, if you want to use methodologies available in TechTide, to focus for your exercise in two methods, the HF interferometry and the GNSS tech gradient. Why? Because this method has the most completed archive. So if you want to search the TID database and search for archive data, these methods are most possible to show to give you complete results. The HF interferometry provide the disturbance potentially associated with TID in the last 6 hours interval, and eddy trend is applied over the ionospheric characteristics, and the mean daily harmonics are removed. So what remains is, as an oscillation, is the effect of large-scale TID. And concerning the GNSS tech gradient, this calculates temporal and spatial tech gradients based on tech maps. And as I said, the tech gradients are precursors of large-scale TID activity. Now, some examples for the 23 of March 2023. Here are products that you can download from the TechTide. This is a storm, and okay, in this timestamp, you can see the result by the HFI method, and this is the result from the tech gradient method. And for a bit later, at 1900, almost, this is the result from the HFI method, and this is the result from the GNSS gradient method. So the GNSS shows a weaker activity because now the bulbs move towards lower latitudes, but the HFI method shows stronger activity. Now, how to get access to the data and models? For the IRI, of course, you don't require any data. The data are embedded in the IRI database. For SWIFT, also, you do not require input data. You just need to run the model through the interface and get the result. From the TechTide, also the data are in the backend database, so you just need to select the product and download the result. But we also provide the possibility for you to download data through the Ionostream NOAA API in case you want to do a comparison or a validation. Now, this is in PITHIA. If you go to the PITHIA portal under data collection, related metadata, data collection, you will find the IRI model, and this model can be reached through two links. We have the older the IRI homepage and the CCMC new homepage. So if you go to the CCMC homepage, you can provide the input parameters. You can provide the latitude and longitude of the station where you want to get from where you want to get the result. If you want, you can specify the hour of the day, the parameter that you want to download. For instance, here I select NMF2, and you can select among the different versions of the IRI and download the data. Now, regarding the SWIFT model is again available through the eScience Center of PITHIA. Using data you can go to data collection, related metadata, data collection SWIFT model, and you can see the location from where SWIFT results are available. SWIFT is a model which is integrated in the European Ionosonde service of the European Space Agency, but this is accessible through you have to have a password to access it. And also, what is available through ACE is only products that are ready, are only plots. If you want to get specific results for any location, for any time period, you have to use the API here and get the results through the SWIFT API. Now, Okay, this is the API. You have to use this endpoint of the API, the SwiftDB forecast pager, and you should specify the start time, the end time, specify the station where data forecast can be provided, and you can just download the data, and that's it. We also provide in this API the possibility for you to download Discover data if you want, magnetic field data from Discover satellites, and you have to use this endpoint, Mac Data Pager, and do the same, specify start and time, and download the magnetic field data from L1. Now, for TechTide is also registered in PITHIA. It is found under data collections, related metadata projects, TechTide, and you can go either to the API or to the web interface. The API is better because you can get results even in image or ASCII mode. Now, this is the endpoint if you want to get HFI data. It's HFI/data/meta. You specify start time, end time. You specify the station from which data you want to use, and select the specific product and execute. You will get you can download the result in a file. Okay, this is how the file. It's a JSON file. This is how the result will look like. Okay, what else? Yeah. Now, for if you decide to work with this data, you can. What my proposal is to concentrate on the recent events. We have many storms occurred lately from January to May. We have strong geomagnetic storms as this one in May, even stronger, a bit stronger in April, and even this month we have two storms. I checked the SWIFT alert, and the SWIFT detected all the storms except from the May storm, from the February storm. In February, we had no alert from SWIFT, and we have to identify why. But all the other storms have been detected by the SWIFT model. Now, for those of you who will work in this group, the proposed study are to collect the results of the forecasted FOF2 and solar wind magnetic field, and try to check what is the observed FOF2, the IRI FOF2, the SWIFT for the next 24 hours, SWIFT forecast for the next 24 hours, and the IMFB components data at L1. Then you can evaluate the performance of IRI and SWIFT models to understand why sometimes one model performs better than the other, and also which of the storms have triggered a large-scale TID in Europe, and this information can be obtained through the TechTide portal. Okay, and these are the station coordinates that you can use for download data from IRI, because IRI asks you for station coordinates. And one additional tip, if you want to download data, ionospheric data, you have many options from the PITHIA portal. You can go to data collections, no Athens edition. In fact, this is something that we have to correct, because this tool, this API here, gives you not only Athens edition data, but data from all European editions. So this is something that we have to collect. In the same sense, the DID base gives you data from all the digisols worldwide, and TechTide also gives you data from most of the European digisols. So you can use this API to download the data from the digisols, and this is how you can download data. You can download everything that it is in the Ionospheric database, and you can get the whole SAO file from this tool with one click. Or if you choose, for instance, PNG, you can get the ionogram image, and I think that's it. Yeah.
Thank you, Anna.
Okay.
Any question for Anna?
Thank you for your presentation. I have a little bit technical question about one of the technique of TechTide about high frequency interferometry. So the question is, generally, for as far as I know, for interferometry, the distance between the observing points should be less than the wavelengths of the observed disturbance. And based on this assumption, what's the lowest wavelengths of the TID this method can determine, detect and characterize?
Yeah, which is okay. This method can detect, in theory, both medium scale TIDs and large scale TIDs. So the wavelength is very variable. It can be from 100 kilometers up to some 1,000 kilometers.
Thank you.
Thank you for the talk. I have a question that's maybe more philosophical, and I guess that the TechTide aim is to detect TIDs in real time. And so, I mean, since TIDs, I think, are a wave, like what does it mean to detect a wave in real time? Like, do you need the full wave to happen before you can issue some kind of alerts? Like, do you see that after some kind of peak in the 8 of the F2 layers, there's always going to be a trough? So that was my question, because I mean, if you consider real time as something that has no a long delay, if you have a TID that is like 2 hours period, how can you confidently affirm that a TID is happening if you need if the period is 2 hours?
Yeah, thank you. This is a very good question of some millions of euros. Now, what we are doing in TechTide is to rely our alerts on the indicators. The indicator is a product that gives you the possibility of occurrence of TID in the next hours. This is the first indication. Now, as soon as this indicator shows a disturbance, then within the next minutes or hours, the other methodologies start to detect the activity and calculate also the characteristics of the TID. Now, we have a new project which is the T-Force project, and this new project aims at providing models for the forecast of TID. This is something that it is mostly based on machine learning, and these models and the machine learning for the machine learning algorithms, we are using data TID detections that are stored in the TechTide database to train the model. So we have a long way in front of us, but considering your question, yes, we cannot detect TID characteristics in real time for the lower latitudes. We can just provide the indication of forthcoming disturbance as soon as the indicators like the GNSS tech gradient or the AATR index shows us that a disturbance starts.
Thanks.
Any other? Okay.
Yeah, Ivan.
It's not a question, it's a comment on both questions. There are two ways you can detect TID. You can look in space. In that case, you need to see the wave. And because of the period, you're absolutely correct. That triangulation only works if the stations are exactly. So you need a very dense network of the sensors in that respect. But you can also look in time. When you look in time, there are several techniques also, and you doesn't have to wait for the whole period to get the beginning, and you can see the TID starts to develop. But with this technique, and we don't have time to explain how it works, you can get both direction where it goes, the period, wavelength, and amplitude. So it's a practically full specification of the traveling disturbance from a single point. Yeah, by looking how the properties of the signal vary in time. But of course, there's a delay. But the good news is that TIDs are not that fast. So if you have a station somewhere strategically placed and you detect it, and TIDs start traveling, you can alert quite a number of operational systems on its track before it, and it's a last resort. The ANAS project, T-Force, will give you a better comfort because it's a alert which comes earlier. Then the last stage is that we see it already. Nobody issued any warnings, but there's a TID in progress.
Of course, here I have to point out that in order to predict which way the disturbance goes, you have also to know background ionospheric conditions, because this is also very critical. The disturbance propagates at different with different characteristics when the ionosphere is very dense, and different characteristics when it's irregular for other reasons. Our life is very difficult.
But we have still a job.
Yeah, we will have for the next decade.
Yeah. Thank you, Anna.
Yes.